Neutron background. Now that's the spontaneous neutrons that the stuff just gives off sitting there. It's important in a nuclear explosion because it can influence when the explosive chain reaction starts in a nuclear weapon. So there's a condition called pre-initiation, or start initiating the explosion too soon. It's widely cited as the key problem for reactor-grade plutonium for making a weapon. And so therefore, it's important that I explain to you neutron initiation so as to explain the difference between reactor and weapons-grade plutonium in a nuclear weapon, in an explosive. Next view graph. So first, what is supercriticality? Well, in order to get the desired explosive yield out of a weapon, the weapon has to be above a certain level of criticality. It must be high enough so that the desired number of fissions occur, and each fission gives off a certain amount of energy, so the total number of fissions is the explosive yield of the weapon. You want the desired number of fissions to occur before the heat from that fissioning causes the metal to expand, moving the atoms apart, lowering the criticality, stopping the criticality, and shutting off the chain reaction. So the explosion, if you will, is a self-limiting process. And there's a race between the fission chain reaction making its explosive energy and the heat expansion turning off that chain reaction. So a chain reaction that leads to an explosion can only happen with fast neutrons. It has to be a fast chain reaction. That's why slow neutrons in a reactor cannot produce a nuclear explosion. The heat expansion always prevents the reactor from exploding. Next view graph. So if you allow pre-initiation, it occurs if the neutrons enter a fissile mass during the implosion, during the assembly of the critical mass, but before it reaches a high enough level of supercriticality. And you may remember that I referred to generations per millionth of a second measuring supercriticality. Well, we're talking tens of generations per millionth of a second in a nuclear weapon. This starts the chain. If you put the neutrons in, say, when it first becomes critical, you start the chain reaction too soon, the heat expansion stops the fission, and you get a very low explosive yield. The chance that pre-initiation happens will depend on the number of neutrons, spontaneous neutrons, that are present at the time of first critical. And I'll show you a graph of that shortly. And so you're not getting to the level of supercriticality that you need for a given explosive yield. Therefore, since the number of neutrons spontaneously produced is a statistical process in the material, pre-initiation results in a statistical distribution of possible yields between a predictable minimum fixed lowest yield and a maximum possible yield. And so then the number of neutrons present depends on the fissile material, and I've already said weapons grade has 100 neutrons per second per gram, whereas reactor grade is five times higher. Next view graph. So the time between when a weapon goes first critical and the needed level of supercriticality to produce the desired explosion depends also on how hard or how forcefully you implode the fissile material, the speed of that implosion. A low velocity implosion in a high neutron background will result in a very low fission yield. That is, the expansion tends to win. But in a high velocity implosion, that enables the fissile material to produce a much more significant yield. So next view graph. Again, implosion, you're squeezing the atoms closer together. When they're very close together, the neutrons can't help but cause a fission before they escape from the material. Next view graph. So here I've plotted supercriticality on the vertical axis in time, typically in millionths of a second across the bottom axis. And the two red sloped lines are to indicate the lower one a slow implosion and the upper one a fast implosion. First critical is where it first comes up out of zero here. And if you think about the number, the supercriticality is generations per millionth of a second of fission chain. then if you integrate, if you add up all of the fissions that occur when you first start the fission chain over time, then you get fissions per millionth of a second time millionths of a second. That is total number of fissions. Therefore, the area, the gray area under each of these curves, is in fact the yield for each of these implosions. Clearly, if you put the neutrons in at zero, you pre-initiate the system, it'll come apart, and the little gray area down at the lower left there is a lot smaller than if you put the neutrons in at the optimal time for an implosion and integrate under that area, and you get a much bigger gray area. You get a much bigger yield. So this is pre-initiation versus optimum initiation.